Hello and welcome back to Calculus 1. We are ready to wrap up the chapter 2, our talk about limits, and what better way to close the chapter than to finally define the limit, right? So we have been using something for 2 weeks now and no clue what it was. So now we are going to write the precise definition for the limit, which is provided in actually 1800s, I think 1850, where the calculus, differential calculus and so on is originating from 1600. 1666 is when Newton had his paper written. So we are talking about the precise definition of the limit. So here we go. Definition. This is on the page 114. So, in which way we are defining this? So what is the meaning of limit x goes to a of f of x equals L? So the limit of f of x is equal to L if for any number epsilon larger than 0, there exists a corresponding number delta larger than 0 such that f of x minus L is less than epsilon whenever 0 is less than x minus a less than delta. Before I explain anything from this definition, I will say that epsilon and delta are letters from the Greek alphabet. Epsilon corresponds to our E, and delta corresponds to our D. You probably seen a lot of Greek alphabet so far. You took trig, so you know about alpha, beta, gamma. Now you know delta, you know epsilon, you know pi, epsilon, you know theta, possibly you know phi, lambda that you used for half-life. So all of these letters that you've seen, and maybe you've seen mu, maybe not. You're definitely going to see mu if you take differential equations. Rho used sometimes for density and things like that. So these are the letters that you might have seen from Greek alphabet, and they actually have one-to-one correspondence to the letters we use over here. You have your R, and you have your M, and you have your L, you have your F, you have your T, P, E, D, G, B, A. So one-to-one is just different letters. All right, so that's so don't freak about epsilon and delta. They're just as good as E and D. All right. Now those quantities are very small, and we can make those quantities as small as we want. In advanced physics, we don't go smaller than Planck's length. But in mathematics, you can go as small as you want. You can put in 150 zeros before you have a value, and it's a very small number. Now, let's focus on this definition. The definition says, for any number epsilon greater than 0, but it's very, very small, there exists corresponding number delta larger than 0, that it's also very small, so that these two equations are satisfied, inequalities are satisfied. Now, the way to understand this is to draw a picture and then talk about these epsilon and deltas in terms of the neighborhood of the... let's take a look. So I have some kind of function. This is my f of x. And then I can pick my value a, which produces L. So as x goes to a, you are supposed to get L. Now remember what I said on the first day when we start talking limits, that pretty much the limit is computing the y value, essentially. So now, where are these epsilons and deltas and things? Well, around L, I'm going to create a tube. Let me use different colors. So, that darker blue? Yeah. So as you can see, I have L minus epsilon and L plus epsilon. Those are the values for these points around L. So L is a number, which is the limit, which is the answer. And now, let's use, I guess, lighter green. We drop this down, and that gives us the a minus delta, a plus delta. Now, I would like you guys to focus on these corner points on the function. So we are focusing on these points here. You see them? You see them? Good. So as you squeeze delta, those points squeeze, and then these points here squeeze towards L. Can you see all of that as a one motion all together? As you squeeze over here, these points draw in and then get these closer, right? Do we all see that? So squeeze over here makes it a squeeze over here, makes it a squeeze over there. Remember that the limit is computing infinitely many points, but never at A. So this blue point is approaching from the left, and you can see that its image is approaching L from below. And this point over here is approaching from the right, which makes L plus epsilon go down. So for any number epsilon larger than 0, which is the separation that we have here, separation is epsilon, there is a corresponding delta, which is this here between black and blue, delta. So for every epsilon you pick, no matter how small, there is going to be a delta on this case, also small, so that when you, look at this, squeeze over here, right? You're squeezing over here because you want to make the difference between the function and the limit. See this f of x? Those are these two puppies over here. When you take the difference of these and you make it smaller, see, this separation here is exactly epsilon. But you now want to take the difference of this, which is exactly epsilon, and make it smaller by squishing it. You're making it smaller than epsilon. So that's the squish, right? So as you squish here, the difference of these is going to squish. So that's the mathematical way to show the squeeze part, where you squeeze these deltas in, and that pushes epsilons in. And that is the situation when you have a limit. And now you have the other situation, which is when you squeeze on x, your y's do not squeeze into L. We can use, let's say, 1 over x, your favorite function, right? Yeah. Just agree, right? Easier than arguing. So, second example is when limit does not exist. So we are going to draw 1 over x. Going to draw 1 over x. And we are going to take a look at a, which is 0. So I'm going to get some deltas going. And as you can see, the deltas bounce into the y. So this is a minus delta, a plus delta. Oh, I just remembered that I used the other blue. And now I change the blue. And now this becomes limit plus epsilon and limit minus epsilon. Now let's squeeze deltas. And I'm going to squeeze deltas by maybe cutting it in half. So when I cut deltas in half, this green is going to do this. Do you see what happened? You squeeze deltas in and the y values get separated more, right? So call this L minus epsilon star, and L plus epsilon star is the second stage. So the more you push in to approach 0, the separation between L minus epsilon and L plus epsilon is going to grow without a bound. You are not collapsing onto a single point like you collapsed into a single point before. Before, you squeeze deltas, they squeeze into L, the limit at A is L, because as you squeeze here, it squeezes there and gives you that location. Now, you take deltas and you squeeze them in towards A. As you squeeze in towards A, the y values go woo apart. And they become infinitely separated. They can be also finitely separated. Doesn't matter. They're not going to end up in the same y location. So, for this case here, we'll say limit as x goes to A of f of x is equal to L. And over here, limit as x goes to A, in each case is 0, of f of x, which is actually 1 over x, does not exist. Because the squeeze did not get there. And that's it. I hope you're not disappointed, but that's it. As you squeeze on x-axis, those deltas, they squeeze the epsilon on y, and it collapses to a point, and you have a limit. Or in the other case, you squeeze deltas towards A, they grow infinitely apart, and you do not have the limit. What did this do to you? And that's it. So, yeah.